Continuing on with class number 10, here's some examples of using the SN curve. A steel rotating beam, this is problem 6.3 in the book. A steel rotating beam test specimen has an ultimate strength of 120 KSI. Estimate the life of the specimen if it is tested to a completely reverse stress amplitude of 70 KSI. All right, so there's that information there. First thing we do is we find the endurance strength, the SE prime. So this is not yet corrected. So that's just 0.5 times the ultimate strength. We go to this graph or use one of the equations associated with it. And for that 120, we find we have an F, this fraction of 0.82. So we use that within this equation to get F times SUT, and we get this coefficient here. And then we're able to use B, and we're able to find this exponent, right? So a negative 1/3 log of that fraction F times SUT divided by SE. Remember that this is really just a curve fit between 2 points on a log-log scale. And now with that 70 KSI, we're able to come up with a number of cycles, 116,000 cycles, which we should really just round to 120,000 cycles so that we don't imply we know more than we do. I would actually go with 1 sig fig if it wasn't going to be so many circumstances where that would be too much of a round off error, right? But you can imagine that, like, if you actually ran through this, it could die within 60,000 cycles or live to be 200,000 cycles. So saying 120,000 cycles is probably going to be a lot better than saying 116. 116,000 sounds like have a pretty good idea of when the thing's going to fail when you really don't. And I shouldn't have said 60,000, but somewhere in there. It's not a very good method. And so I wrote these in small little tiny things right there. But if you take, let's see, we're at 120 and you multiply it by 0.82. Let me do that right here. 0.82 and 120 is it come out to, about 98, right? So just below 100. So that looks like it's about right. And we already said that we're going to use 60. So you could, counting on here, you go 20, 10, 20, 30, 40, 50, 60. So right here is a 60, and it cups right there. So there's our line. And then we're going to say, well, we tested it for 70 is what we came into there. So here you go. And so right in there is about right. It looks about right. So graphically, we need to have that be able to find that. So here's another, moving right along. Here's another problem from the early part of chapter 6. Steel rotating test specimen has an ultimate strength of 230 KSI. Estimate the fatigue strength corresponding to 150 kilocycles of stress reversal. And then repeat this, but now to do it with 1,100. All right. So what I decided to do, I guess I'm actually doing problem 6.6, but because problem 6.6 refers to 6.5, we did that. So I just want to do it in metric. So yeah. So we're also going backwards, right? So here we have number of cycles, and we want to go backwards. So we take that 1,100 megapascals, and here's the SE prime, and then we could look up from here and find out that we have looks like it's close to 0.79. We could get a bit more accurate with the equations. And now we could put that into this equation for the coefficient A, and find the exponent B. and now work with this equation right here to find out what stress will result in 150,000 cycles. And then as I had up here, here's the 1100, and then right around here should be whatever that was, 0.79. All right, so I should be able to do that in my head, but I'm not gonna. 0.79. So 869. So yeah, that's probably right. So zeros be 200, 300, 400, 500, 600, 700, 800. Yeah, like right in there. That makes sense. There's 900. Sure, could have done that in my head. And then also, whatever that is it 550? Yeah, 550. So it's kind of halfway in between, right in there. Sure enough. And if we had the number of cycles, what would we say, 150,000? So here's 100,000 right there, right? And so here's 200,000. So here would be about the amount that we could expect on this graph from being 150,000, roughly. So we're somewhere in here. So that's where that's what these problems are, just using these graphs. I'm going to make a separate video for the modifying functions. So we'll talk about those in a second. This was a short video of 6 minutes. Yay.